properties such as interleaving materials. So here's a schematic setup of showing the interleaving concept. Different fabrics that can be used to interleave that are studied in this research as the carbon fiber veil, carbon nanotube veil, and silver-coated carbon nanotube veils. And on the left side, as you can see, this is a material without the interleave. And what happens is essentially you insert interleave material between the different layers to improve the thermal properties. So these are some of the common methods known to use to find the thermal properties. The first method being the transient plane source, which is pretty much you have your two materials and you set the sensor in between it, and the sensor heats up, which is a double nickel spiral coil, heats up, and you measure the temperature with respect to time, then you can apply the thermal equations that they will feed transient flow and find the thermal properties. The second method, hot wire method, is similar to the transient plane source, except you have a wire, and shown here, a wire that's embedded in the material along with the thermal couple that measures the temperature as time goes, and then again you can use the thermal equations that will solve for the thermal properties. The 3 omega method is very similar to the hot wire method, but the main difference from that is the fact that the wire is not embedded in the material, it actually lays on top of the material and sends the heat source through that way. And that's the common method used in conducting thermal conductivity of a foil. And then the fourth method that I'll talk about is the flash and DSC method, which is the method used in this research. And it's by far the most simplest method because, and it gives very accurate results, because in this method you find the thermal diffusivity, the specific heat, and you measure density, and then from those 3 properties you can multiply those together to get the thermal conductivity. And this is just simply the thermal diffusivity equation rearranged to solve for thermal conductivity.
And that's good. Use a pointer at least people can see.
Oh, got it.
And the pointer helps.
All right. So one of the first objectives, using the flashline DSC method, using this method you have to find the 3 properties that will make up the thermal conductivity. The properties that are specific heat, thermal diffusivity, and then the density of the elements. So that will be the first objective of this research, to find those properties. From there, we can move on and calculate the transverse thermal conductivity by using the equation that was shown before, the simple product of these 3. The materials given for testing is the item 78552-1 carbon epoxy, which is used as the base material, and then the 3 interleaving modified versions. And that material will be interleaved with carbon fiber veil, carbon nanotube veil, and silver-coated carbon nanotube veil. And what we want to see is how these materials interleaved in there affected the thermal properties and whether or not it improved it or didn't change or decreased it or not. And then from there we want to establish a set of equations, a general set of equations that will you'll be able to calculate the thermal conductivity if you know the temperature or at a given set of temperature. So you input the temperature, you get what the thermal property is at that temperature. And then assess the impact of the different tools. From here, this is a general setup of a basic composite. The composites we got from NASA are all unidirectional. As you can see, the fibers, what that means is the fibers all lie in the same direction, so it's not cross.
Would you mind using your pointer to show? Yeah, okay. Fiber direction.
I thought it was a laser format.
No, those are requests. Yeah, I think with that doesn't work.
So what unidirectional means is the fibers all lie in the same direction. So as you can see, throughout this material, they're all laying in one direction along the X1 direction. And how this affects the material is, if this material was stacked, if you thought of this as a layer, and you were stacking these layers to make a thicker composite, the X2 direction and the X3 direction will exhibit the same properties because it's going to have the same setup. So that's one thing we can notice. So in finding the thermal conductivity through this layer in the X3 direction, we actually find the same property that's actually through the X2 direction. So this is just a schematic kind of showing how that works. So the approach that's being used is, again, the flash method and the DSC method. The flash method is used to test the thermal diffusivity, The material, the DSC, which stands for differential scanning calorimetry, is used to test a specific heat, and then we measure the density by its mass and use geometry to find its volume, and then that's how we discover the density. And getting these three parameters, we can then calculate thermal conductivity, which is given right here. And that is just a schematic of the flash method and how it works. And I'll go into more detail when we get to that section as to the process and how it works. These equations are just the general equations that are used with the device. They're built into the software and how it's used to calculate the properties.
And define those parameters also.
So you have alpha, which stands for, which is the up here, which stands for thermal diffusivity. And I'm going to go into more detail when I get to that section. I'm split to break them up. And this equation was developed by William J. Parker back in 1960 at a conference, and it's the equation that's been used. Clark and Taylor, and I'll get more detail about it. Clark and Taylor developed a new parameter that kind of fixed and go deal with the radiation heat loss that takes place when you're running the test and gives a better accurate answer of the results. So you have, again, the thermal conductivity, which is signified by K, thermal diffusivity by alpha. The CP is denotes specific heat, and then this symbol here, rho, is density. These are corresponding units for the four different parameters. So carbon epoxy composite. This is the material that was given from NASA as a carbon epoxy base material. The IM78552-1 is the actual material that was given, and the bells that they used in the lead and the material were all purchased from Nanolabs, and they actually fabricated all the materials there at NASA and then sent them to us. They sent 4 panels that were approximately 50 by 35 millimeters, which is about 2 inches by 1.5 inches. They're very small. And from there, we cut samples out using a hole saw and a drill press for the flash line method and the DSC method. These two methods both use a cylindrical shape specimen, which is shown here, and they're placed in the machine and you run it, and I'll go into detail as far as the process of that. The materials all had different thicknesses of the panels. They're given here. The baseline was 0.9 millimeters. The carbon fiber bell was 1.08 millimeters. Carbon nanotube 1.52, and then the silver coated carbon nanotube was 1.96, which was by far the thickest. And so this schematic here shows the layout in which we were cutting them, and so we keep track of where it was and which samples we what. The larger circle are the samples for the flashlight method, and the smaller circles are the samples for the differential scanning calorimetry method. So here are pictures of the samples that were actually tested. As you can see, with the baseline material, we tested 1 inch and also half-inch samples. That was done to just see if there was any variance in between the size, if the size made a difference, which it shouldn't have, and it didn't. So we tested to make sure that wasn't a factor in finding material properties. All the other approved materials were all half-inch samples, and we shaved off the top layer, grinded it down with very, very fine sandpaper to get rid of the mold release layer that was indented, because the way the flash line method works, it measures the temperature across the back face, and that surface must be very flat or closely as flat as possible, and the mold release left indentions on the surface. Down here is the schematic showing when we cut it, it shows the fiber directions and which way they're going. And so as we can see, it is clearly going through the transverse. We'll be measuring transverse direction properties. Again, for a specific heat, it's the same similar thing. We cut it with a hole saw and a drill press. These are smaller samples, just a small fragment of the specimen. So we took optical images after we got the samples cut. We cut smaller pieces, fragments, little rectangular pieces, potted them in the epoxy, and so we can get clear optical images of the specimens. This is the baseline picture showing off the fibers and the X1, X3 direction. So that's along the fibers, and also perpendicular to the fibers, so it's showing the ends of it here cut through the fibers. And what can be seen here in the dark regions are the void content within the fiber due to lack of resin flow. And as you can see with the interleaving materials, you can clearly see the layers in which they're built with interleaving kind of going through it. These are the next two materials, the carbon nanotube and the silver coated carbon nanotube optical images. And if you can note, going between from the carbon fiber belt to the carbon nanotube, the amount of void did increase. It's given by the dark shaded region. And we'll discuss that later as far as results. So the measurement of thermal diffusivity, again, the flashline method was used. The device was an Answer Flashline 2000. Thermal diffusivity, for those who don't know, is just simply the speed at which the heat transfers through the material. So it's how fast the heat travels the material. And this device uses, you have to know the diameter, you have to know the thickness, and you have to set the parameters in which you're going to conduct the temperature test. You input these into the software, and then you begin the test. Equation given by Parker with the correction factor given by Clark and Taylor is seen here, with the L standing for the thickness of the material, the T half-time, which is found from doing the test, measuring the amount of time it takes for the back face, so the top face that is not being heated, to reach its maximum temperature is the half-time it takes for that. And Clark and Taylor coefficient is a factor that they included, which was expanded. It takes into account the back face when it reaches 75% of its maximum temperature over when it reaches its temperature, the half-time, or the time it takes for it to reach 25% of its temperature. And the temperature that we test this material is from 20 to 100 degrees Celsius. That's about room temperature to boiling water. The reason being is when you extend beyond 100 degrees Celsius, you get into the phase where it starts to go through its glass phases, so it starts to change phases, which will change properties, so we stay away from that. Here's a picture setup of the lab and the experiment setup. This is the device that the actual Answer Flashline 2000 used to conduct the thermal diffusivity test. You have the software that it runs into that measures and keep track of the half-time as well as the temperature. And so just to kind of explain how this works, this area down here is where the heat source comes from. It shoots a pulse of energy or heat through the front face. This heat then travels through to the back face where the IR indicator measures the temperature and the time it takes for it to reach its maximum temperature. It takes that time. The experiment follows the ASTM standard E1469, which just details how to conduct the experiment and when you should throw out the results, because the setup says that it has to fall, your half-time must fall in between 10 milliseconds and 1,000 milliseconds or 1 second in order to get accurate results. If it's outside of that, then the results are no longer accurate. You have results, but those aren't the results for that material. You should then either make the material thinner or make it thicker, depending on what the half-time is. The results we get is the thermal diffusivity versus temperature, and the alpha P is the Parker's method. The alpha here is Clark and Taylor with their additional factor involved. And below are just some of the features of the machine and how it's set up. So again, this is just a block diagram kind of explain what I just said as far as you have the laser or bulb